I expect that my two other colleagues on the panel are going to have subtle and detailed and fascinating things to tell you about the workings and failings of specifically human memory. My own contribution is going to be a good deal more abstract than that. I'm going to be interested in human memory here only as a special case of a more general category of recording, which is a very broad term that encompasses photographs and compact discs and fossils and scratches and bullet holes and human memories and fingerprints and videotapes and what have you. And I'm going to be talking about the very broad and very crude and very fundamental question of why there can only be recordings of the entropic past and not of the entropic future. And there's something a little bit awkward even about the business of confining oneself to questions of the time asymmetry of recording. So let me back up a little further. Still, the general consensus among people who concern themselves with these sorts of questions, I think, is that our everyday experience of being in the world presents us with three, at least on the face of it, more or less distinct categories of temporal asymmetry. There's a category of what you might call ordinary or familiar sorts of physical asymmetries, which refers to the asymmetries covered by the Second Law of Thermodynamics and the preponderance of outgoing over incoming radiation and stuff like that, the fact that smoke spreads rather than recollecting into cigarettes, the fact that things burn and don't unburn, the fact that soup cools and doesn't spontaneously heat up in warm rooms and stuff like that. No, there's not supposed to be a display. I didn't have a chance to print out my notes, and I'm just using the computer to give me my speaking notes. This will be a low-tech talk. So that's the first category. A second category of what you might call asymmetries of epistemic access. This refers to the fact that the kind of epistemic access we have to the past is very different from the kind of epistemic access we have to the future. The kinds of things we can know about the past, the detail with which we can know them, and the means by which which are available to us to get to know them are very, very different from the kinds of things we can know about the future and the detail in which we can know them and the means available to us by which we can get to know them. And then there's a third category of what you might call asymmetries of intervention, which refers to the fact that all of us walk around with every millisecond of our lives, that we have a very profound conviction to the effect that by acting now we can affect the future but not the past. All of these are, at least on the face of it, puzzling when you put them beside the fact that's been referred to a number of times so far in this conference, that that all of the serious candidates for fundamental, universal, microscopic, exact dynamical laws of nature that anybody has seriously entertained since Newton have all shared this property of perfect time reversal symmetry, in a radical and exact way refusing to make any fundamental distinction whatsoever between past and future. Okay, so it seems to me that if one can, if one can get a one-line lesson out of the past 20 years or so of discussions of these asymmetries, it's that, and this is something that Sean alluded to in his opening talk, it's that a greater and greater optimism has emerged that these three asymmetries turn out to be very intimately related to one another, and that all three of them turn out to have a common source in the structure of statistical mechanics, and that the business of thinking about one or the other of them in isolation from the rest, as I'm apparently being urged to do by the title of this session, turns out to be more likely to confuse matters than to elucidate them. So I guess I'm going to want to resist the urging to talk about this separately a little bit, and talk not so much about the phenomenon of memory or even recording in isolation as about how that phenomenon fits into the more general phenomenon of differences between past and future. Good. The business of making all of this explicit is a big project, and it's one that's still very much underway, and it's one that's the work of a increasing number of different investigators. And I can only give you the tiniest hint of what that project is about in the half hour that I'm allotted here. But I'll try, if I can, to be suggestive, at least, about the general shape that a project like that might take. Okay, so let me start off, having said all that, by reminding you of the basic logical structure of classical statistical mechanics. Statistical mechanics, as most people here know, begins with a postulate to the effect that a certain measure on the set of possible exact microconditions. Let's talk about the classical case to keep things simple. A certain measure on the set of possible exact microconditions of any classical mechanical system, a certain very natural-looking measure on those set of exact microconditions, be treated as a probability distribution over those microconditions. The measure in question here, as I said, is in fact the simplest imaginable measure on the set of possible exact microconditions of whatever system one happens to be dealing with, the standard Lebesgue measure on the phase space of the possible exact positions and momenta of the Newtonian particles that make the system up. And the thrust, and here I'm skipping over 100 years of work, the thrust of all of the beautiful and ingenious arguments of Boltzmann and Gibbs and of their various followers and collaborators was to make it plausible that given any true thermodynamic law to the effect that macro condition A evolves over such and such an interval under such and such external circumstances into macro condition B, then the overwhelming majority of the volume of the region of phase space associated with macro condition A on the above standard measure is taken up by micro conditions which are sitting on deterministic Newtonian trajectories that pass under the allotted circumstances at the end of the allotted interval through the region of phase space associated with macro condition B. That is, the upshot of everything that the pioneers of statistical mechanics were trying to argue, if those arguments work out, is that thermodynamic regularities are what they are because they express what the overwhelming majority of exact microscopic trajectories, at least majority according to this standard measure, are doing. Okay. And if these arguments succeed, and if Newtonian mechanics were true, and of course all these arguments can be updated without too much trouble to quantum mechanics or field theory or string theory or what have you, if these arguments succeed, and if the basic dynamics, which we're taking here to be Newtonian mechanics, is true, then the above-mentioned probability distribution over micro conditions is going to underwrite enormous swaths of our empirical experience of the world. But there's a famous trouble with these arguments, which is that all of these arguments work exactly as well in reverse, okay? That is, the trouble is that all of the above-mentioned arguments entail not only that, say, a half-melted block of ice sitting at present in a warm room is going to be more melted 10 minutes from now than it is at present, but they also entail that it was more melted 10 minutes ago than it is now, and hundreds of millions of analogously bizarre claims about the past. And it doesn't seem like an exaggeration to say that we're as sure as we are sure of anything whatsoever that these latter claims are false. And there's been a sort of canonical method of patching that trouble up, which is to supplement the dynamical equations of motion and the statistical postulate that I mentioned above with a new and explicitly non-time reversal fundamental law of nature, the thing that Sean called the past hypothesis in his introductory talk, which is a hypothesis to the effect that the universe had some particular simple, compact, symmetric, cosmologically sensible, very low entropy initial macro condition. The patched up picture then consists of the complete deterministic microdynamical laws and a postulate to the effect that the distribution of probabilities over all of the possible exact initial micro conditions of the world is uniform with respect to the Lebesgue measure over those possible micro conditions of the universe which are compatible with the initial micro condition specified in the past hypothesis, and that there's zero elsewhere. And with that amended picture in place, it begins to look like the arguments of Boltzmann and Gibbs are going to make it plausible, not only that paper will be yellower and ice cubes more melted and people more aged and smoke more dispersed in the future, but that they were all less so, just as our experience informs us in the past. With that additional stipulation in place, to put it another way, the arguments of Boltzmann and Gibbs are going to make it plausible that the second law of thermodynamics remains in force all the way from the end of the world back to its beginning. What we have from Boltzmann and Gibbs then, and that's very crudely speaking what one might call the consensus picture of the microstatistical account of the first of these three asymmetries that I described a few minutes ago, the asymmetry of what I was calling, this is not a good name, but what I was calling ordinary physical processes. Okay. What we have from Boltzmann and Gibbs, then, is a probability distribution over possible initial micro-conditions of the world, which, when combined with the exact deterministic microscopic equations of motion, apparently makes good empirical predictions about the values of the thermodynamic parameters of macroscopic systems. And there's a question, a sort of philosophical question, about what to make of this success. We might take this success merely as evidence of the utility of that probability distribution as an instrument for the particular purpose of predicting the values of those particular thermodynamic parameters, or we might take that success as evidence that the probability distribution in question is literally true. And note, and this is something worth pausing over, that if the probability distribution in question is literally true, and if the exact deterministic microscopic equations of motion were literally true, then that probability distribution combined with those equations of motion would necessarily amount not merely to an account of the behaviors of the thermodynamic parameters of macroscopic systems, but in some principled sense, it would amount to the complete scientific theory of the universe. Because the two of them together assign a unique and determinate probability value to every formulable proposition about the exact microscopic physical condition of whatever physical things there may happen to be. If the probability distribution and the equations of motion in question here are regarded not merely as instruments or inference tickets, but as claims about the world, then there turns out not to be any physical question whatever on which these elements turn out to be jointly agnostic. If the probability distribution and the equations of motion in question here are regarded not merely as instruments or inference tickets, but as claims about the world, then there are only two logical possibilities. Either they're false, or they're in some sense all the science that there can ever be. And precisely the same thing will manifestly apply in the more, to any probability distribution over the possible exact microconditions of the world, combined with any complete set of laws of the time evolutions of those microconditions, such as quantum mechanical ones, or field theoretical ones, or string theoretical ones, and so on. Good. Some of us who work on the foundations of statistical mechanics have lately taken to calling this probability distribution over trajectories the metaculus, which is a name taken from a Coen Brothers movie where the psychotic brother of the protagonist is working on a notebook which he refers to as the metaculus, and which he describes as a probability map of the world. Okay. Anyway, I want to look into the possibility that this metaculus, that this probability distribution we have from Boltzmann and Gibbs, or something like it, something more up to date, something adjusted to the ontology of quantum field theory or quantum string theory, or what have you, is true. And this distribution turns out to have simple and perspicuous and, I think, very illuminating things to tell us, not only about the first of these asymmetries, about the second law of thermodynamics, and about the preponderance of outgoing over incoming radiation and so on, but also about this symmetry of epistemic access, and also about the asymmetry of intervention. Good. What it's going to amount to explain this or that as a mechanical phenomenon of nature is to show how it can be extracted, at least in principle, by means of the appropriate sorts of conditionalization from this probability distribution we were calling the metaculus. That's what's going on, and that's all that's going on, according to this way of thinking, when we explain why a certain projectile lands on this or that particular patch of the surface of the Earth, or how an atomic clock works, or why ice melts in warm rooms. And these explanations, and this is important to note, these explanations don't require any metaphysical or conceptual or linguistic or phenomenological distinctions at a basic level of any kind whatsoever between past and future, or even, for that matter, between time and space. And the thrust of all the remarks I want to make today is that, insofar as I can tell, there isn't any principled obstacle standing in the way of precisely this sort of an explanation of the asymmetry of our epistemic access to the past and future, and to the apparent susceptibility of the future, but not the past, to influences from the present. The business of actually putting these explanations together, as I said, is a large undertaking, and I'm not going to be able to tell you too much about it. But let me suggest something of the lines along which people are thinking. Let me make a distinction to begin with between two different procedures for making intertemporal inferences, for making inferences from one time or set of times to another time or set of times. So here are two distinct such procedures. Procedure one. Start with some collection of facts F about the physical condition of the world at some particular time T. Put a probability distribution which is uniform with respect to the standard measure on the phase space over all of the possible micro-conditions of the world which are compatible with these facts F, which you know about T. Evolve that distribution forwards or backwards in time by means of the microscopic equations of motion so as to obtain information about the physical condition of the world at other times. Call this, let's make up a technical name for this, call this inference by prediction if the other time in question is in the future of T, and call it inference by retrodiction if the other time in question is in the past of T. Good. I don't have time to argue this. Here's something I think is true. The entirety of what we justifiably believe about the future, I suspect, can in principle be obtained by prediction from the entirety of what we justifiably believe about the present. But retrodicting from what we believe about the present is a notoriously terrible way of drawing conclusions about the past. This was the trouble with the original Boltzmann proposal that I referred to before. One of the lessons of the work of Boltzmann and Gibbs is that retrodicting from what we know of the present is going to imply that the half-melted ice in the glass of water in front of me was more melted 10 minutes ago than it is now, and that I have never looked younger than I do now, and that Napoleon never existed, and so on and so forth. Okay. Second method of inferring from some times to other times. Start with two collections of facts, not one, about the physical condition of the world, F1 and F2, where all the facts in F1 pertain to some particular time T1, and all the facts in F2 pertain to some particular other time T2. Put a probability distribution which is uniform with respect to the standard measure on the phase space over all of the possible microscopic histories of the world that are compatible with F1 and F2 and the microscopic equations of motion, and use that distribution to obtain information about the physical condition of the world at times in between T1 and T2. So you have a sandwich of pieces of information from which you infer further pieces of information about the temporal region in between the two pieces of bread in the sandwich. Call this, to distinguish it from inference by prediction or retrodiction, call this inference by measurement. Inference by measurement has the name it does because it's modeled on the logic of measuring instruments. Measuring instruments are the sorts of systems which reliably undergo some particular transition when they interact in the appropriate way with the system they're designed to measure, only in the event that the measured system is, at the time of the interaction, in one or another of some particular collection of physical situations. Physical situations we would refer to as states in which the measuring device is properly calibrated and plugged in and ready to do its measurement. Okay? The record that emerges from a measuring process is a relation between the conditions of the measuring device at the two opposite temporal ends of the interaction. The record-bearing conditions of measuring devices which obtain at one temporal end of such an interaction are reliable indicators of the situation of the measured system at the time of the interaction, only in the event that the measuring device is in its ready condition, the condition, that is, in which a device is calibrated and plugged in and facing in the right direction and blah, 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 at the interaction's other temporal end. The sort of inference one makes from a recording is not from one time to a second time in its future or past, as in the prediction-retrodiction case, but rather from two times to a third, which is in between them. And note, and this is one of the crucial observations here, and this is an observation that Sean very briefly alluded to in his opening talk. Inferences by measurement can be immensely more powerful. Inferences by measurement can be immensely more informative than inferences of the predictive-retrodictive variety. Think, just as a simple toy example, of an isolated collection of billiard balls moving around on a frictionless table. And consider the question of whether or not, over the next 10 seconds, billiard ball number 5 is going to collide with any of the other billiard balls. The business of answering that question by means of prediction is plainly going to require a great deal of calculation, and that calculation is going to require as input a great deal of information about the present. It will require, in particular, a complete catalog of the positions and velocities of every single one of the billiard balls on the table. But note that if we happen to know, by hook or by crook, that billiard ball number 5 was moving 10 seconds ago, then the question of whether or not billiard ball number 5 happens to have collided with any of the other billiard balls over the past 10 seconds can be settled definitively in the affirmative without any calculation at all, merely by the single binary bit of information that billiard ball number 5 is currently at rest. And note that whereas the information that billiard ball number 5 was moving 10 seconds ago and that it is at rest now is going to suffice, completely irrespective of how many billiard balls there are on the table, to settle the question of whether or not billiard ball number 5 was involved in a collision over the past 10 seconds. The amount of information we're going to require in order to determine, by means of prediction, whether or not billiard ball number 5 will be in a collision over the next 10 seconds is going to rise and rise without limit as the number of balls on the table rises. Good. But there's an obvious puzzle about how it is that inferences by measurement can ever actually manage to get off the ground. The game here, after all, is to look into the business of making inferences from one time to another. The game, more particularly, is to look into what we can know about the complete history of the world from the vantage point of the present. And in the context of an investigation like that, the facts that it's going to be appropriate to think of as unproblematically given to us, the facts from which it's going to be appropriate to think of these inferences as starting out, are presumably going to be limited to facts about how the world is now. Consider, for example, the case of the billiard balls. If I happen to know that billiard ball number 5 was moving 10 seconds ago, then I need know no more of the present state of the entire collection of billiard balls than that billiard ball number 5 is currently at rest in order to conclude that billiard ball number 5 has been involved in a collision over the past 10 seconds. But how is it that I ever do happen to know that billiard ball number 5 was moving 10 seconds ago? Well, presumably by measurement. Presumably that is because I have a record of it. But how is it that I know that the purported record in question is actually reliable? How is it that I know that the measuring device which presently bears the purported record of billiard ball number 5's having been in motion 10 seconds ago was in fact in its ready condition at the appropriate time prior to 10 seconds ago? Presumably by means of another measurement. And before you know it, a ruinous, world-devouring regression is underway, which can only be stopped by means of something we're in a position to assume about some other time, something of which we have no record, something which cannot be inferred by the present by means of prediction, retrodiction, something to which a sufficiently relentless investigation of the ultimate grounds of our knowledge of almost anything we know about the past must eventually lead back. The mother, as it were, of all ready conditions. And very briefly, and this is something that requires an enormous amount of justification, which I'm not going to be able to begin to give you here, very briefly, the thought is that there's an obvious candidate for just such a mother of all ready conditions sitting right at the center of the standard statistical mechanical account of the second law of thermodynamics in the form of the past hypothesis. The thought is that it's because the fundamental physical laws contain a past hypothesis but no analogous future hypothesis that facts about the present can be so mind-bogglingly more informative about what's already happened than they ever are about what's going to happen. The thought is that there can be measurements of the past but not of the future precisely because there is something in the past but nothing in the future to put an end to the regress. Good. And it turns out that the flip side of all this has a lesson in it about the asymmetry of intervention. Think again of the collection of billiard balls, and suppose, and this is what's going to stand in the context of this very simple example, for a past hypothesis that billiard ball number 5 was moving 10 seconds ago. What we learned about that sort of a collection of balls in the discussion of the asymmetry of epistemic access was that whether or not ball number 5 is going to be involved in a collision over the next 10 seconds depends on more or less everything about the present condition of every single one of the balls on the table. But whether or not ball number 5 has been involved in a collision over the past 10 seconds can, at least in some cases, be settled by the present condition of ball number 5 all by itself. And so, very crudely again, almost anything about the physical condition of the world at present can affect whether or not ball number 5 will be in a collision over the next 10 seconds, but almost nothing about the physical condition of the world at present, nothing in this particular case, save the present state of motion of ball number 5 itself, can affect whether or not ball number 5 was involved in a collision, over the past 10 seconds. And so there are, as it were, a far wider variety of potentially available routes to influence over the future of the ball in question here. There are a far wider variety of what you might call causal handles on the future of the ball in question here than there are on its past. And all of this is going to generalize. What it says in my notes is generalize straightforwardly. That's bullshit. But it's going to generalize if things pan out to cases of worlds which are much richer and much more complicated and much more like our own. And this is how one can begin to link these three asymmetries, the thermodynamic asymmetry, the asymmetry of epistemic access, and the asymmetry of intervention together. But all this, as it stands, is at best only a suggestive beginning, and it raises at least as many questions as it answers. Let me just indicate one. What's worried almost everybody about this account, in particular, is that it seems to imply that the distinction between our control over the future and our control over the past is a matter of degree, whereas that distinction presents itself to us in our everyday experience of the world as something absolutely and infinitely sharp. And this has been much discussed over the past 10 years or so since this program was first sort of conceptualized, and much has been learned about it over that period, none of which I can tell you about right now, but maybe we'll have a chance to discuss it later. Thank you very much.